And I'll hang out after class is over to look at people's work too again, if you want a hand. We just had somebody in the breakout room. We're figuring out how to map out like a huge building just by starting to have a huge, like a big cube shape, and then figuring out where one corner is going to start, and then working our way out from there and adding details around it. All right, we're not doing isometric though. We're doing orthographic now. Orthographics. So on one paper, I'm going to keep a running list of the orthographic rules, which are written into the assignment, and the rules are also listed on one of the pages in that sketching and drawing resource packet that I have linked in the agenda. And I also put graph paper in the agenda. If you wanted to print graph paper out, you totally can, right? I also left some graph paper out in the classroom. But you know, drawing on graph paper, unless the grid lines are nice and light, right? If you just if you were to just put them through, like print it out in the printer and they came out real dark black, you want to run the job again, the print job again, but print it out grayscale or reduce the amount of the ink so that it comes out real light. That way, when you draw over it with your pencil, you'll be able to see a nice contrast between your pencil and the grid lines. All right, so an orthographic drawing is the other one we need besides, well, there's 4 assignments, but in terms of when you show off a 3D product in industry, to show the form, you use isometric, but to show the functional side of it, how it's built, how it's made, we have orthographics. And the goal of an orthographic is that somebody could take your drawing, and when they're done with it, when they're done looking at it, they could reproduce exactly what you had built to the exact same sizes with all the same parts, features, details, everything. Right, so that's the goal of an orthographic. From an isometric, people can't build what you made. It's just a colored picture. They have no idea how big it really is. They can't see the bottom of it or the back of it or inside of it. But an orthographic is going to tell us all the information that we need to reproduce that object. So the word orthographic, we know that a graphic is a picture. Where do you guys think the word ortho comes from? Do some etymology work. What does that word mean, orthographic? Where have you heard ortho before? No, we have Invisalign. Remember orthodontists?
Does it mean straight?
Yeah, straight. The orthodontist straightens your teeth, right? How about an orthopedic surgeon? They straighten out broken bones. So one way to think of orthographics are straight pictures. So if they're 2-dimensional, they're going to be head on, facing us in the exact perspective that we're looking at them, which is straight on, so it's 2D. But ortho, besides meaning straight on, will also take on the meaning perpendicular to. So these objects are head on, but in orthographic sketch, rule number 1 is going to be that it is a 3-view drawing. For us, there's going to be 3 views. If we were to map out all the faces of our 3D object, and let's say it was cubic. Let's say it was cubic. You'd have 6 sides to a cube, so we could have up to 6 views if it was a cube, this object. But we're only required to have 3 views, and those 3 views can be like your top view, a front view, and a side view. All right, and these 3 views, when we do this, they're always going to end up on graph paper. And what I mean about ortho meaning perpendicular to, even on pictures that are 2-dimensional, if I pull the rules to the side for a second, and I were to show you like a Lego piece. We know the isometric view of a Lego, baseline, perpendicular line, 30s. All right, so if that's an isometric, and I were to add color to this thing, whatever. That's the isometric. The orthographic for this picture, I'm just going to whip one out like real quick. I'm not going to follow any of my own rules except for the 3-view drawing rule. I would take my paper and break it into quadrants. And then I would hold my object down flat in its front position for the front view. And say it was this oil can. And I'd put the object down like I'm looking straight over the top of it. And this oil can makes a rectangle shape. And it has this protrusion up here, and this protrusion and this cap. So from the front view, if I made this my front view in this quadrant, so I put the can here. I'm just sketching. This is all done with a ruler and a pencil, exactly the size or to a scale if what you're drawing is going to look smaller than it is in real life. But that's the front. There's this piece that sticks up. Here's this top and that cap. It's got this ridge down here and this ridge here. All right, there's the front view. So what I mean by orthographic and perpendicular to, when you go from your front view to your side view, you take your object and you rotate it 90 degrees or perpendicular. So from this quadrant to go to this quadrant over here, I rotate it 90 degrees. Now I've got the side profile. And so that side profile would line up right next to this, right next to this. There's the cap, there's the protrusion. Right? But from the side view, it's a little skinnier because the side of the can is skinnier than the width of the can in the front. And then from this view, when I want to go to the top and look at it like a bird's eye view, again, I flip it up 90 degrees. Now it's straight up and down. And here's my view looking straight down. See, when I'm straight down, I can't, if I only have is this view, I have no idea how tall this is at all. I have no idea if I only had the one view. I can't see the sides, the front, the back, or the bottom. So to be orthogonal to something means perpendicular to it. As well, all these pictures are straight. They're head-on, they're two-dimensional, they're not skewed in any way. But you can see here in this 3-view drawing, I've got the top, the front, and the side, and each view is oriented where it's facing it's perpendicular. You make a perpendicular move 90 degrees to go from one view to the next view. Here, flip it up 90 degrees to the top. All right. So if this were your paper, this was the object that you were doing, you'd have 4 quadrants like this. It would all be on graph paper. And then at the end, you would put a title box somewhere. And we'll go over what a title, it's just a place to put your name and the date and stuff like that. It's just a thing everybody does on engineering drawings. All right, so we got the orthogonal part. That from any one view, you spin it 90 degrees and you've got the other view. So back to my rules though. We're going to be required to have 3 views done on graph paper. The second rule will be that all lines are drawn with a pencil and a ruler. With a pencil and a ruler. It's nice having a clear ruler because you can see through it and makes it easier to draw and to be able to see what's underneath of yourself there. And if you don't have a mechanical pencil, a number 2 Ticonderoga is just as good. And I recommend not just having a sharp pencil, but if you have a box cutter, I wouldn't use an X-Acto razor for this because X-Acto razor blades flex too much. But it's nice to have an actual sharpened edge that has 4 or 5 sides to it. By rotating this a few times when you pull, and you get these nice little points that you can ride on when you're drawing. It always is nice to have a nice, fresh, crisp pencil. I'd probably sharpen my pencil 15 times over the course of a drawing. All right, the third rule here is going to be that our views have alignment. What's alignment mean? If I went back to this thing and I put these 3 views in these boxes, but could I put these boxes in if I put these pictures in the wrong quadrants or arrange them wrong, it wouldn't look right. So right now, the way these three views are aligned, they are aligned and it works. The reason I know is if I go from any one view and I take the sides here, and if I were to continue up, I run into the sides of the top view. And if I were to come from this direction and go sideways, there's the top of the can, there's the top of the protrusion, there's the top of that cap, there's the bottom. The centers line up here. That all works. But if I had drawn this out incorrectly, and I put the views in the wrong location, you spot it right away because you'll be able to see that the alignment's not there. So let's do this, but incorrectly. You know, so there's correct alignment over here. So if I move the order of these views around, and let's say I put the side view here, let's put the front view here. And let's put the top view here. I know the centers here are lined up, but the sides don't line up. So if I go from this view up to here, I'm running right into the object. Not good. If I come from over here, I miss the object completely. No good. And it doesn't work because that would not have been a 90-degree rotation into the next view. Does that make sense to everybody? All five of you I can see? Four of you? All right, nice. Thanks. I appreciate at least a couple of you leaving your cameras on so I can get some feedback. All right, cool. So we've got a bunch of rules here now. I'm going to give you a couple more rules, and then we're going to give you something to try and see if you can try following the rules that we have so far. So the reason there's a bunch of other pencils out there besides the number 2 pencil, you use these for Scantrons in school, right? Yeah, this is what they use on a Scantron. Those machines read that. There's also a number 3, number 4, number 5, number 1. It goes all the way up to 11 or 12 or something. And there's different hardnesses and softnesses. And originally, before there was CAD software where you would draw things and then make them 3D in the computer, the prints, whether they were orthographics for a product or they were blueprints for a home or architecture, every type of line that you would draw in your pictures would use a different type of pencil. And that's how you would distinguish between the object itself and dimensions being different and notations being different. So there's a few types of lines that we're going to draw all with the same pencil because you only have one pencil. So what are you going to do to make contrast on different types of lines that you have to draw with one pencil? We're going to make our object lines, the lines that are actually for the thing we're drawing itself. The object itself, we're going to draw that in nice dark pencil strokes. So object lines are going to be drawn dark. And after object lines, dimension lines, when we add dimensions to the object, dimension lines, we're still going to use a ruler for those, but they're going to be done in a very light pencil stroke. So you can still see it, but it's lighter in contrast to the object lines themselves. So knowing what we know now with these 4 rules so far, all right, we haven't learned how to add dimensions yet. But what I would like you to do is, you don't have to use up a whole sheet of paper because we're just sketching right now. You don't have to be on graph paper right now, right? This is just practicing these other rules, except for the ruler and the graph paper. We don't need to worry about a ruler or graph paper right now. We're just trying to figure out how to lay things out properly. And so I want you to try to draw up now would be a can of soup, okay? But you're not even going to get 3 views out of it. You're going to get 2 views out of the can of soup. All right. So if you had a quadrant, where would you put your two views and how would you align them for an orthographic drawing of a can of soup? You guys work on that for a minute while I plug in my other headphones. These are dying. All right, I just switched into that other camera view. If you lost me in the gallery, you could pull up your second window to see what I'm doing. All right, you got it now where you can see my picture up in the corner. Is that how it's set up? Yeah, okay, cool. On 3D, I know what this can of soup looks like. But how about in different views? Well, you're going to label views like we have top, front, and side, and you just give the view the name that you think is the most appropriate for it. So you wouldn't want to call the top of a can of soup the front because people wouldn't think of it that way. I got a cup here, but that would be a natural top view. That would be a natural front view or side view, right? Front view for this cup being the same thing as the side view for the cup. All right, so that 90-degree flip is going to come this way. I could be here, and I could flip 90 degrees to be like that. Or I could go from here and be 90 degrees here. So what you could have on your paper right now could be, for the can of soup, this could be the top view. And right below it could be the front view. If I didn't have the top view for the front, if this is the front view of the can of soup, you have no idea what this is. It could be a cinder block. Until you have the top view, you don't know that that's a cylinder, right? And if all I gave you is the top view, you don't know what you're looking at as a quarter or a 20-foot tall column. No idea. So the multi-view drawings give us the ability to put the pieces together from each face. So that could be my top and my front. You could have laid yours out just like this. That would be great if that's what you did. Or you could have also laid it out like, there's your top. You could have laid it out to be orthogonal. You could have taken the can, went that way with it, in which case the can of soup would look like it was laying on its side, right? That would work because these pictures are aligned. I got the alignment, that's cool. However, I would have probably gone with this view or with these over here because this is its more natural front position and that's the more natural top. So even though this is correct and it's aligned, it's probably not the most natural position to call these to see this in. I'm going to lead with the view that is the most natural view. And that's why I put the front down here. All right, so we've got these views. Now how do we get to the dimensions of this? Now for this, I'm going to try to actually draw this up. Oh, that reminds me. Again, I know this isn't a can of soup, it's a tapered cup, but if I was going to draw the cup from this view, from the front view. I see the lip of the cup. I'd see that it tapers, but but it would be flat on the top and flat on the bottom. Does that make sense? Flat across the top, flat across the bottom in this view. Why is it flat on the bottom, flat on top? A cup's round, Chris. It is. A cup is round, but if you look at it from the front view, it is flat on top, perfectly flat, and it's perfectly flat on the bottom. If that's the case, I'm not going to see any semblance of a circle in this picture. It just looks like a trapezoid. I bring that up because somebody was drawing a car tire in the other class, and this was their front view for their car tire, right? But then for their side view of the car tire, instead of being a rectangle right next to this, they drew it like this, like rounded. I know if you overinflated your tire, it would round up here at the top and round at the bottom from a front view, but the car tire sits flat on the road. So it would be flat on the top and flat on the bottom, and that side view should just be a rectangle. All right, so let's add dimensions to this can of soup and figure out if we're showing all the details or not. To save time, before I put my quadrants in, I'm just going to fold my piece of paper in half and do it in half again. Cool. My quadrant, and let's get the top of the can of soup. Again, I'm only doing this for the sake of speed. When you're doing it in real life for your assignment, it's going to be on graph paper with a pencil, every line drawn with a pencil. So you're drawing these object lines nice and dark for the can. Maybe you run over it with your pencil 2 or 3 times on the ruler, and then nice and dark for this. Am I missing any features right now in a can of soup in these two views? I'm going to label them in all capital letters, by the way. All prints are always all capital letters when we draw. Or I'm sorry, when we write words, which I guess because lowercase gets sloppy. That's going to be a rule we add. Is there any other details to this we need to add right now when you look at a physical can of soup? Is it totally smooth on the top and on the face, the can of soup? No, if you look up close, that can of soup actually has little ridges in it. Little ridges put into it all the way around it. They're so minute, they actually get hidden behind the label, but they're there so that the can doesn't crush so easily. You know, so I'd have to express that in this picture. If you felt the top of this soup can, doesn't this have like a bump to it? The top of the can, isn't there like a little lip? Yeah, that's where when it's being manufactured, the can, another piece of metal gets pushed on top, and then a machine folds it around the edges, and that's what makes that lip. So that lip would have to be noted in here. If that's the, that lip it's real thin, but it's still a measurable part. So I'd have to have a concentric circle in there to represent that lip. And I'll probably see that lip here in this view too. And I'll see that little lip down here at the bottom as well. That's not the label I'm drawing. That's the metal lip on the edge. Okay, cool. So now I've got my object drawn nice and dark. You know how in a math textbook, you want to show the dimensions on something, you just put it right across the middle. You're like, oh, that's 5 inches across. Right? You know, you do that in a math textbook, they would do that. We'll never, ever put dimensions on our object, ever. We always have to put them off to the side. Otherwise, when your orthographics get sent to the manufacturer and they're going to make your thing, they're going to think the number 5 is supposed to be engraved into your lid. So they would you'd never write the dimensions on something. Only like math textbooks do that. So for us, our dimensions have to be off to the side. Now I'm trying to dimension every part, but I don't have to put every dimension in every view. If I tell you the width of the can one time here, I don't have to tell you the width of the can up here in this picture. As long as that dimension gets out there one time, that's all we need. So let's start with the height of the can. All right, and I'm doing this in green, but you're gonna do this in a lighter pencil stroke, so it makes contrast with the object lines. So your dimension lines go like this. You put a termination point at the top where the line's gonna stop, and another termination point at the bottom. And then we draw an arrowhead and another arrowhead. And let's say this can is 7 inches tall. I'm going to draw these lines with my ruler, and I'm going to leave a break in the middle, and that's where I'm going to put 7 inches. So dimension lines are always done lighter with a termination point, fancy word for it tees off up there and it tees off at the bottom at right where the object stops, right where the object starts. And then you put an arrowhead in there. There you go. Now we have the height of the can. All right. Does this little lip here have a dimension to it? Sure. How thick do you think that is in real life? I don't know, 1/16 of an inch, maybe a 32nd of an inch. Well, Chris, I can't write that dimension there. It doesn't fit. No problem. We're going to use a light pencil line, and we're going to pull off from here, off to the side, pull another line off to the side. And I'm going to put little termination arrows in there, like I'm trying to draw this dimension line, but it doesn't, what I want to write in there doesn't fit. And so I'm going to use a third type of line called a leader line. And a leader line, you treat like it's a dimension. You do it nice and light pencil. But a leader line is anytime I want to tell you about something, but I didn't have enough space there to write it myself. So since I couldn't write the dimension in there, I'm going to pull off like this and make a little space for a note and say that that is 1/32 of an inch. And I might as well dimension the top lip too while I'm there. It's the same thing. Bring that one out on an angle, 1/32 of an inch. Cool. How about my top view? There's two different ways I could give you the same width for the can. If it's a perfect circle, there's two ways I could tell you how wide the can is. What would one dimension be? Like one way be to do the dimension. I wonder how wide this is now. Well, I don't have to tell you how thick. No, I guess I do. I told you how tall the lip is, but I haven't told you how wide the lip is in this picture. So we're going to need to know that little lip thickness again. So I can probably come out again here with these leader lines. I'm trying to draw you this dimension, but it doesn't fit. So I pull out and say that's one, maybe it's thinner than it is thick. So maybe that's only 1/64 of an inch. That's how thick that little lip is from this point to there. But how about how wide the can is? Well, one way I could do it is I could put the width here, come up from the circle, come up from this. As long as I'm using a lighter line, it's no big deal to make a nice long line off that point, the widest point on the circle. Come up and then make my termination lines. My termination lines come in and say this can is 4.5 inches wide. I could do that, but another thing I could have done to show you this dimension, the width of a circle is the same thing as its diameter. So I could have, if I were to just draw you a second version of what this could look like, I could have went right off the top of the circle with a leader line and said, hey, this whole circle here is a diameter of 4.5. So either would be acceptable. That's a diameter symbol. Showing you the width this way, coming off the object's widest points, 4.5, or just touch down to the tip of the circle with a light line and write in 4.5. So leader lines can be used to give you I'm sorry, like down here, a leader line could be used to give you a dimension in a space where you can't write anymore. But you can also use a leader line just because you want to give people a note about something. All right. So I don't know what type of note I might want to add to this can, but maybe maybe I want you to know the material that it's made out of. So I can pull right off the can itself from somewhere. with a lighter pencil line, and I'm going to make an annotation. Annotation is a fancy word for a note. And I'll say something like, what are tin cans made out of? Tin. All tin body of sheet metal. So it's probably made of sheet metal. Because if the person's going to reproduce this, they need to know what material it's made out of. So I even get real specific. I don't know exactly what kind of sheet metal and how thick and what the quality is of it, but all those things would get included in an annotation somewhere I could add off. So this is not bad for a can of soup. It's actually still missing a couple things, but we're going to show you that in the next picture. So for a can of soup, this would suffice. That's why I don't want you picking a plain cylinder for your assignment, because it will only be 2 views. I want you to pick something that has some hard corners in it so that you can have 3 views in your drawing. All right, so can of soup. I'm going to add a couple rules to the rules list while you try going from can of soup to paper towel roll. Now this is going to be a paper towel roll or like kind of like a toilet paper roll, whatever. But I want you to, it's a cylinder and it's going to have a cardboard tube going through it. All right, so it's just like a can of soup, except there's this cardboard tube going through it. Can you now draw this paper towel roll in 2 views and start adding dimensions to it? So depending on how you're approaching this paper towel roll, if you're used to your paper towel roll being wide, like long, like it's hanging up, like the ones in the bathroom are hanging up and they come down, you pull from them. In that case, your front view is like the paper towel roll is wide like that, you know. That could be your front view, and your side view would actually be the, that round profile there. That's if you consider this to be the front view because of the way the paper towel roll will be sitting in real life. But if you have a paper towel roll that sits on your desk or on the kitchen counter, those rolls stand up and down. If that was the case, then I would draw it where my front view is standing up and down, because I'm imagining that's how you would be walking up to the paper towel roll, right? And I'd be pulling paper towels off. And then my orthogonal flip cannot go over here. That doesn't have alignment, right? That does not align. So my top view has to go up above it up here. So this would be appropriate. All right, you keep going. I'll add another rule. So back here, this paper towel. I know from like a top view, whichever one of these you went with, this or this, doesn't matter. From a top view, I know I want to see the paper towel roll. Doesn't that cardboard tube have a thickness to it? Sure, it's whatever, it's a fraction. But if that's the case, then I have to draw two circles, concentric circles, because the person needs to understand that there's a thickness there on that paper towel roll, and I can dimension it. But right now, if you look at these two views, it looks like I've got a rubber band laying on top of I don't know what. You know what I mean? Or it looks like there's some ring or something laying on top of a circle. If this was a quarter or a ring laying on top of this cardboard or laying on top of this thing, then from the front view, I would see something that would look like if that's the top and it has if that was a quarter, then from the front view, I would see that quarter expressed as a little bump sticking up in the other view, right? But it's not a quarter. It's a tube that goes through. So what do we need to do to show people that there's a tube that goes through there? I can't draw this tube like this. If I just put a line like that down that view and told you, well, yeah, it's aligned with that, you know, that's it. They would think there's a ruler or something glued onto the front of this. How do I let people know that these lines are actually inside of the thing? We're going to add a rule here. I said object lines are dark, dimension lines are lighter, and we're going to use this as a dimension line or for our dimensions, and they're definitely off to the side. I said you can have leader lines anytime you need to put an annotation or a note or put something somewhere where something doesn't fit. Those leader lines usually pull off on an angle. In drawings, you see them keep the angles consistent at a 45. If that angle is going to bump into another view, then they'll pull it out on a 30 or on a 60-degree angle. You could take orthographic drawing class for a whole year and learn how to be an actual person that produces the prints. But we're just trying, and there's a bazillion rules, but we just want to have like around 10 rules that we can follow so that anytime we produce something in this class, we at least have some standardization to our approach, but it's not to the detail that you would learn if you're an architect or something. I wrote here another rule was to have all capital letters with any words we put in here, whether it's the title or any notes, everything's in all caps. So the next rule I need is that dotted lines, hidden features, things that are hidden or that are inside of something, they're going to be done with a dotted line. So anytime you see a dotted line, you know that that's a feature that's hidden. Dotted lines for hidden features. Therefore, if I were to correct it up here, and again, yours could be next to each other like mine, or you could have them like this, just like this picture was. All right, but I'm ignoring that one right now. So now, whatever I drew as my concentric circles over here, when I'm on my graph paper, this would line right up with the dotted lines I'm going to put here to show that that's a tube that actually goes all the way through. And just like I have a concentric circle here that show that there's a thickness there, I need to put a double set of dotted lines because the wall of this tube has a thickness that you would see in this view, except it's hidden, so it's all dotted. So you got like double dotted lines. Now, if I want to start dimensioning this, I can tell you how thick this is from this picture or this picture. Doesn't matter which one I decide to do, but you're going to need to know the thickness in between these two dotted lines or the thickness in between these concentric circles. So I think the way I'm going to approach this is I'll tell people how wide this is here. Maybe this is 11 inches. Make sure you break it in the middle. Tee it off, arrowheads. So we got that width. I'm even going to tell people the height over here. Arrowhead, bring that down, I don't know, 6 inches. But when it comes to this inside here, if I just tell you the thickness of the wall here, we'd be good. So, or I could tell you the what's it called? The diameter of each one of these circles. So I could pull out a leader line and I could tell you the diameter of the outer circle and the diameter of the inner circle. If you know the two diameters, then you'll be able to figure out everything else. So that could be like, oh, the diameter of this one is this, but the diameter of this one down here is this. Another way to do this, instead of telling you the two diameters, would be to just give you the distance between the center circle and the outside circle. If I did that real big, if this is the view here, here's these concentric circles. Again, forgive me for not being able to trace everything to go fast enough. You know, you have to do all yours with pencils and trace everything straight. But I could do a thing like this. I could come off here with a, let's go off to come off to the side here from the top of the line with a leader line, and then come off from the other circle with a leader line. And I'm saying, okay, so what's the distance between these two places? I pulled off to the side with my leader line. My dimension does not fit inside there. So I'll pull off another leader line and say, yep, that thickness is 1/64. And I'd probably have annotations all over this thing, like telling me how many times the paper towel wraps around the roll, how many paper towels are on there, that this inside here is cardboard, and that this out here is a certain thickness or weight of paper. So let's show another way to dimension something that can also help you save time. And we're almost done here, folks. Let's say I was reproducing this like a whiteboard marker. The whiteboard marker's flat on the bottom. You got this tube. All right, and coming out of the tube, the tip there, and then there's the chisel tip of the actual dry erase marker. But if the cap's on it, I have to forget that. If it's got the cap on it, I'm gonna have to draw it like I know this is terrible, but that's a dry erase marker. and if the dry erase marker, it has all these different pieces to it, like this bump here, the cap, and then the long tube. And I'd have to draw dotted lines to show that there's more to the body of this marker that comes up into this part. You know, the rest of the shape of that marker would have to be done in dotted lines because it's behind the cap. Even the chisel tip that you write with. And then I'd probably have to put double dotted lines because the thickness of the plastic tubing, there is a thickness to it. So the rest of this would have to be a dotted line underneath the first one. That's what I didn't do with the can of soup, was add dotted lines to show you the wall thickness of the can. So we have something like this. Now, how can I add dimensions for all these pieces, for the body, for the cap, and the tip on the cap? That's 3 different dimensions. Instead of having 3 different dimensions set up, I'm going to make one long dimension. I'm going to come down from each point that I'm going to be bringing you a measurement for. And I'll put my arrowheads in here, and I can say the body of the thing is just making stuff up. 5 inches from here to here. So I'll call this a compound dimension. It's when you put more than one dimension on a single dimension line. So this part's 5. That means this part might only be 1 inch. And then I can't really fit that nubs dimension there, but I'm still going to draw the arrowheads, and I'm going to bring out a leader line and say that that little nub sticks out 1/4 of an inch. So here I have one long dimension line, but I was able to break it down into pieces, the 5 inch, the 1 inch, and the little piece, the 1/4 inch, I couldn't fit in there. Oh, you know what I forgot to show you guys? I think I showed you guys this in the last class. Didn't I show you the magnified view in the last class? It has nothing to do with orthographic, but it's like another drawing technique that you can use. Remember when I did the miso soup, I had the can of soup, and on the can I had a picture of me, and I wanted to show you that I was sewing something by holding a needle and thread in my hand. And I had the shirt there like that. And I had the patch on the shirt, right? And like I wanted you to be able to make this out, but it's hard to tell what you're looking at here. So if I were to take like a red marker or some other colors that would make contrast, and I were to draw a circle just around this part, and then I came off the object and I made that circle much bigger, that would be called the magnified view. You know, this might be helpful for somebody on your process drawing or in your brainstorming morph chart. This could be a technique you could use. And I would redraw this. There's the arm, there's the hand. There's the needle. Now you can see the eye of the needle, and you can actually see the thread coming down. And there's the shirt. Now you can really make out that it's a patch because you can see all the little stitches on the side, right? And I'm starting to reproduce what's inside this circle. So you can get in close and see it. You reproduce it. All right, magnified view. I meant to tell you that after I showed you cross-section view. All right, so I'm gonna throw out a couple objects, and you do this. You don't need to use the ruler just for the sake of time, but see if you can map out. And this can be on plain paper. It doesn't need to be on graph paper. See if you can map out a top, like a 3-view picture for a couple objects. Let's try stapler. Let's try candy bar. We could try a box of tissues. Stapler, candy bar, or box of tissues. Start with a quadrant, figure out which view do I want to show off first, make that my front view, and see if you can get your views aligned with one another. Just the alignment's the big part here. The alignment is the big part. Don't worry about the dotted lines and all the hidden stuff. We're just worrying about trying to align our views right now. That's what I want us to practice for any of these objects, stapler, candy bar, or box of tissues, so that you get the practice of aligning something. Let's see, candy bar. Probably somebody the way you hold the candy bar, like a Snickers bar. I imagine when you're used to seeing a Snickers bar where you see the packaging wide ways like that. That's how they're usually advertised. It says Snickers across here. So maybe I'll make this my front view. I know it's like it's a side profile, but I'll make this the front view for a Snickers bar. So if this is my front view, and maybe a Hershey bar. So that would be my front view, like a rectangle, and I can see the chocolate broken up into sections in there. If that's my front, and I do an orthogonal flip 90 degrees, then my side view, or my top view, I guess we call that, and we can call that side. Call this front. So my side view would be right above it. And I would just see those little indentations like this, but they don't go all the way through the candy bar. You just kind of see in the middle where you can break in between each section. And then I have a choice. I can put my third view here or here. It doesn't matter as long as I draw it the right way and align it. So if I go from here, orthogonal flip up, I could put the top view of the candy bar right there like that. Box of tissues. What do I want to be my most natural position for the box of tissues? Probably the front. This is going to be one of those boxes that are longer and shorter. This is what I wanted. I'm just drawing the isometric of it now. That's the isometric. So thinking about it like this could probably be like the front view. Then this could be the top. Then this could be the side. It's nice to look at it in 3D first and then name the face that you want to draw where. Like front. Okay, that's okay, cool. Now that I figured that out, now I come over here and I'm like, all right. So front view is a narrow rectangle. Top view is directly above it. If I draw the tissue sticking out here like this, then see the top. I see the tissue like a wavy little line like that. Almost looks like mustard going on a hot dog or something. Got that little plastic part the tissue comes up out of. Inside the tissue box, and there probably would be dotted lines that show the stacks of tissues that are still sitting inside there. I would need to tell you the thickness of the wall. Can't do it here, but if I use the whole paper, the whole 11 by 17 graph paper, it'd be very easy to draw it, probably in full size, actually, like a 1-to-1 scale, and be able to get all those details. And then from the side view, trying to get this face here. So I could put it here like this. This would be an acceptable side view where I just see the little piece of tissue sticking out. But I know it aligns and it all works out, but it's kind of more natural to me to have the side view here, in which case it would look like that. That's the tissue sticking up. The top of the tissue lines up with the top of the tissue, the bottom with the bottom, all this stuff's lining up. Now I'm going to map out something, the more difficult one here, the stapler. Ugh, 3D. Rather than risk getting the perspective on the stapler wrong, I'll just start with like a like an isometric picture. This is not orthographic, but this is just helping me figure out what it's going to look like. Maybe it's like rounder up here like that, the stapler. And it's probably got a base here and some pieces that stick out. Maybe it's even taller in the front and then gets shorter toward the back. And it's got all this, and there's like the little piece that does the stapling. All right, I think I got it. We could do this as the, let's do this one as the side. This as the front. We'll do this as the top. Ook. I'm looking at it, go, okay, I want that to be the side view. I want to do the top of that, and the front is that. So if that's the case, let's start with the front view as that first one. Looks like a cheeseburger, but that would be the stapler if I'm just staring at it from this direction, front facing, and just looking at these details in the front. So my side view can be right next to this. So I'm lining this up on my graph paper with this top edge. Stapler coming down a little bit. There's this piece, does the stapling. That with that, that with that, this edge with that edge. And there's this little bracket I have sticking out here on each side. You'll see that bracket right there. Cool, so where do I want to put the top view now? Well, I could lay it out up and down here, or I could lay it out right over this one. So I think I'll do it like that. I'll pretend I got the stapler and I'm flipping it 90 degrees. Now I can see this bracket that sticks out here and sticks out there. Now I can see the brackets on either side here. This is the top I'm pushing down on. So I can't see any of these other things inside here. I won't see any of that. But to do it all properly, I'd have to have dotted lines. So I would see dotted lines in here that show the rest of that mechanism that holds the staples. I'd probably see that mechanism expressed as dotted lines here, so you can see the rest of it. From up top, there's this rectangular piece that's holding the staples inside. Yeah, this thing tapers from the front to the back, like it gets smaller toward the back where the axle is. I also drew it tapered from a top view. Doing this, even whatever on another scrap piece of paper and laying everything out and figuring out, is this going to take up my whole page now? Because that's what you want it to do on the real thing. You want it to take up the whole page, right? You'll always have an open quadrant with nothing in it because you only have to show 3 views. In that open quadrant, you could put a scale, a title box. A title box is just a fancy word for a box that has information in it. So you can leave your name on the back because you're not worried about your name being there. But you could put the date, you could put the name of the object you're drawing. One of the best things to put in here, though, would be a scale. Put a scale inside your box. Did I draw this stapler? If it was 11 inches long in real life, did I draw it with an 11 inches here on the graph paper? If I did, then I could say that my scale is 1 to 1, right? Or 1 block on the graph paper actually equals a 1/4 inch in real life, which the blocks on the graph paper might be a 1/4 inch, that could be an 1/8. But if they're a 1/4 inch and I'm drawing the object the same size, In real life, that quarter inch equals a quarter inch. I could do that. I could draw a block and say one of these blocks equals a quarter. But if you were drawing a whole house in isometric, I'm sorry, if you were drawing the whole house in orthographic, you'd be scaling that house down like 50 times to make it fit on a piece of paper. If that was the case, your scale might be 50 to 1. 50:1, or if one block was a quarter of an inch in real life, one of these blocks was a quarter of an inch, then that would be one block equals 200 inches in real life. Something like that. Whether you're for scaling up, or I'm just saying this is two ways to write the same thing. You want to include a scale. So you really are measuring your thing out with a ruler, or a tape measure, or calipers, or some measuring tool, because in order for it to work on the graph paper, it's got to be the exact same dimensions that things are in real life. So we're going to close class off here, and I'm hanging out for anybody that wants to show me your work or run things by me. No big whoops, but I want to show you what my expectations are for this drawing. In the assignment itself, I put links to old Jamboards where people had posted pictures of orthographics. And I tell you, there's some up there that are garbage, and you'll see one or two of the group that are like really nice. It'll be easy for you to tell which ones are garbage and which ones are nice. I like to put a mix up there. So you're looking for the people that were able to follow all of these drawing rules that we came up with, and trying to dimension as many things as possible. I'm gonna stop sharing for a second. We'll be out of here in 1 minute. Oh, somebody had a question. I'm just going to go on the internet and look up a cell phone and see what the orthographic of an actual cell phone was. What it actually looked like. I need a wireless keyboard. I don't want to scare you with this one. Let's just show you this one. Open link in new window. Ugh, garbage. There we go. Just blow this up. Oy vey. Well, you can see on the left-hand side here, all these dimensions. You can see the leader lines they pulled off with. You can see these termination points for dimensions. You can see how they left the line open in the middle to put the dimension. You can see a leader line being used here to show a feature, but there's nothing that's left undimensioned. Everything is dimensioned. The thickness between one piece to another, the distance between one feature to another. And so you can't do a cell phone as you're drawing, but something with as many details as a cell phone, you wouldn't be expected to have 100 dimensions on it like they would in real life. But you can't just come in with the length, width, and height. You have to show that you've made an attempt to seek out every part or feature and that you try to give it a dimension. All right. Even the round corners up here, like these round edges on the phone, are drawn round, and they put a radius dimension instead of diameter. They put an R for what the radius of that thing is. You can see center lines here. We don't use them. Center lines notate a perfect circle with crosshairs. We're not worried about that. All right. And so try not to worry about being perfect and try to just focus on your one object. Map it out on a piece of paper, how you think it should look, how you think you're gonna lay it out. All right, I'm gonna stop the recording now. I know this was a long class.